Hi students, good morning. Today we'll be talking about electrophoresis. Alright, now this is a very new series of videos where I'll be taking on competency 11.16. Okay, so if you have your competency module, you can check. The competency includes practical demonstrations of all the various processes that you need to know. So that includes pH meter, paper chromatography, TLC, polyacrylamide gel electrophoresis, ABG, ELISA, autoanalyzer, quality control, DNA isolation, so on and so forth. So I'll be covering each and every one of them in subsequent videos, but today I'll be taking on protein electrophoresis. Alright, since it's a practical demonstration class, this means you need to take down the notes, and these are the exact format that you need to write in your practical copies. Okay, so I'll be giving you the notes, and since it is a demonstration, I'll also be showing you the experiment, okay, in video. So let us first take down the note. So you should give a heading: separation of serum protein by electrophoresis. So this will be your heading. So depending on the method of your choice, you can give a more specific heading: separation of serum proteins by paper electrophoresis, or separation of serum protein by gel electrophoresis, or by Agarose gel electrophoresis. Okay, so aim of the experiment is to separate serum protein by paper or Agarose gel electrophoresis. It will not be both. Okay, it will be either one. Okay, it can be agar gel electrophoresis too. So what's the principle of the experiment? Okay, please take these notes down. It will be easier to understand while seeing the experiment video. So as you can see, I'll just read it out for ease of your writing. Electrophoresis is the migration of charged particles in an electric field. So this part you already know, alright, from your +2 knowledge. Whenever electrical field is applied, any particle which has got a charge will move to its opposite electrodes. A negatively charged particle will move towards a positive electrode in an electric field. Okay, so anions, that is negatively charged electrode particles, will move towards the positive electrode, that is anode, and the reverse. Okay, so anions move towards anode and cations towards cathode, right? We will use this principle in our experiment. So the next line is: in alkaline medium, protein exists as anion. Okay, hence it will move towards the anode. Not only proteins, I am just telling you one more thing: DNA. Even DNA electrophoresis, gel electrophoresis will apply the same principle. It is negatively charged under physiological pH, or we will create a buffer in such a way so that DNA behaves as a negatively charged particle. But over here we are talking about protein. So different proteins have different isoelectric pH. What is isoelectric pH? A particular pH in which the protein will have a net positive and negative electric charge. Okay, so if we calculate the buffer in such a way that it matches the isoelectric pH of the protein, okay, therefore at that pH different proteins will carry different charge. Alright, some protein which matches exactly with the isoelectric pH will absolutely have negative charge, while some other protein, depending on the pH, will carry different amount of charge. That different charge will lead to what? Will lead to the differential movement in the electric field. We will use this principle. So a protein, different protein will have different charges, and so different charges will move in different speeds. So we will use this method, and we will give some time. Imagine it as a flat race. Okay, some protein can run fast, some protein can run slow. So if I blow the whistle and I tell 5 proteins to run as fast as you can within say 1 minute. Depending on their charges, that is the speed, some protein will be running excess fast, so he will score first, some protein will lag behind. So if I freeze during some time during that run, we will easily see how the proteins are separated. Okay, so different proteins have different isoelectric pH. At a particular pH, as determined by the buffer used. Different protein carry different charges, hence vary in extent of migration in an electric field. This property is used to separate and identify different serum protein. Okay. Now, not only the charge, their migration also depends on few more additional factors. So, what are they? They are net charge, that you know, size of the particle, mass is very important. If two proteins carry the same charge, the heavier protein will be running slow and the lighter protein will be running fast, right? The strength of the electric field, okay, the pH of the medium and the viscosity of the medium. So, these are the few factors that vary. However, in our experimental settings, the pH, the viscosity and the strength of electric field will be fixed. So, the migration will depend on the charge and the size. So, what are the requirements for the experiment? Okay, the requirement for any electrophoresis experiment is number one, an electrophoresis tank, a chamber in which the experiment is conducted. It is followed by an electrophoretic support, a support medium, a platform on which we will apply our sample and on which, that is the ground on which the contestants will run. So, it will be either cellulose acetate strip or agarose gel slide or any agar gel, depending on the type of electrophoresis. Okay. Power supply. Power supply is another electric device that will be connected to the electrophoresis tank. I will be showing you shortly. Filter paper, Wattman filter paper number 1. Please note down in your note, the purpose of this filter paper is to connect the gel with the buffer. Okay. It may or may not be used depending on the chamber design. The next is the buffer. So, either it will be barbitone buffer or tris buffer. Okay. So, the barbitone buffer is made up of sodium barbituriate and barbituric acid, and tris is a complex compound that is available commercially that you need to dissolve and you will get the buffer. Okay. So, buffer preparation protocol will be standardized depending on lab to lab. Next, we will need some dye. Okay. So, the dye for protein electrophoresis are two. Number 1 is Competency Brilliant Blue, COOMASIE, or in few lab they use amido black. Okay. This dye may also be used. So, either Competency Brilliant Blue, the name is Competency Blue, it is also known as Competency Brilliant Blue or amido black. Thereafter, a fixative, that is sodium hydroxide, and a decolorizing or a de-staining agent. Okay, it is also known as de-staining agent. It is made up of methanol and glacial acetic acid. Okay. So, these are the few requirements for an electrophoresis to run. What next? Let us see the procedure, how it happens. When I show you the video, it will be much more clear. So, first the gel should be prepared. Okay. Depending on whether it is agarose or cellulose acetate paper or agar, if those are agar or agarose, they first need to be heated, boiled and then cooled. Those are available as solid flakes or strips, but if they are boiled in water, they become a semi-solid gel-like compound. First boiled and then cooled. So, preparation of gel is done before the electrophoresis is planned. Okay. So, if I plan an electrophoresis experiment today, I need to prepare the gel half an hour back or overnight, a night back, depending on the scenario. So, remember, write these steps because you need to write them in your practical copy and then you will be able to visualize in the video. So, electrophoresis tank is uniformly filled with barbitone buffer on both sides. Okay. I'll be showing you how a tank looks like. Just write this down. Now, after that, there is one step which is missing over here. You need to write the first. You should write after preparation of the gel is placed on the electrophoresis tank. Okay. After the gel is placed, the tank is uniformly filled with barbitone buffer. Okay. Sample is applied transversely by an applicator. Okay, we need to apply the samples on the gel, right? Filter paper. Okay, this line you may choose to write or not write depending on the procedure that is shown, okay, or that you prefer. So, buffer soaked filter paper placed as wicks in one side of the paper overlapping and other side dipped in buffer. I will show you exactly what I mean. Okay, just for now write this down. So, the filter papers are cut in strips, small strips. They are dipped in the buffer. One side of the filter paper is in contact with the gel and another side is in contact with the buffer. Okay. Next, the chamber is connected to power supply and it is run at a constant voltage or constant current depending on the standard protocol of the lab. After the completion of the run, the electrophoresis chamber is switched off, the power supply switched off and the filter paper are removed. Then the gel is placed in the staining solution. Okay. It is placed first in the staining solution and then it is placed in a destaining solution. Over here again, it might be confusing to you before you see the exact video. Sometimes we pre-stain the samples. If we stain earlier, we don't need to stain it further, we will directly destain it. But in most cases, the samples are first applied with little amount of dye to get an idea where the sample is and then staining and destaining are applied. And then finally, it is after it is destained, we do the densitometry to check whether normal sample run or the abnormality of protein in the sample. So, I will repeat again. What are the steps? I will be repeating these again after I show you the video. Okay. So, first preparation of gel. Next, the gel is placed on the electrophoresis tank. Next, buffer is filled in the electrophoresis tank. Next, thin strips of filter paper are connected to one to the gel side and another to the buffer side. We will connect the electrodes. We will run for some amount of time. Then we will stop the power supply. We will remove the gel. We will stain it with the staining solution. We will remove the stain with destaining solution and then we will do the densitometry analysis. Okay. So, how the analysis looks, I will tell you later. Now, see, this is how this is a schematic diagram. Okay, let's visualize first. This is a schematic diagram. I will be showing you the real deal. So, this is an electrophoresis tank. This is how the electrophoresis tank looks like. Okay, this is the support medium. Remember, you need to draw a schematic diagram in your practical copy also. So, now it's a good time while I am telling you to also draw the diagram. So, this is the electrophoresis tank and this is the gel. Okay. First, the gel is placed on the medium and then buffer is filled on both sides of the tank. Okay. Note these black lines are electrodes. Okay, and there is a connecting point of electrodes to the power supply. So, black must be connected to the black and red must be connected to the red. As a convention, mind it, the negatively charged electrode is black and the positively charged electrode is red. We will always apply our sample, whether it is protein or DNA, towards the negative side, because being negatively charged, it will move from negative towards positive. Okay, so this is the sample. So, what happens, see the filter paper. So you see in some electrophoresis tank, the buffers are not in direct contact with the gel. So just to complete the circuit, we soak filter paper and we dip one end to the buffer and we dip one end and we contact one end to the gel. So current will run from positive electrode via the filter paper through the gel via the filter paper to the buffer, and it will complete the circuit. Remember, that is the direction of the current. This is a direct current. Okay, so it's a constant flow. In case of AC alternative current, it will run back and forth. So we will not use AC. Always we should use DC, and this is what the power supply does. It is connected to the main AC source and it converts AC to DC. The gel will run from negative to positive, mind it. So that being said, we now let us see how this is done in real life. Mind it, this is a very schematic diagram, okay, just for illustration purpose. Nowadays it's available in automated fashion. So most of the labs do it in automated manner. I will be showing you that automated electrophoresis only, where you don't need to apply this filter paper, okay, because we will directly dip the gel in the electrodes, in the buffer which are dipped in the electrode. So let us say I will show you both agarose gel and I will show you protein electrophoresis also. So I think it will clear your cloudy concepts. So let us first see the protein electrophoresis, okay. So it's a video from DDS Diagnostics. So they are showing serum protein electrophoresis in their lab. Now all these materials are available as commercial kits, or they can be placed in, they can be prepared in lab. So this is the power supply, okay. So let us see how it's done in step by step manner. First you will have a kit insert or a protocol, with the help of which you need to prepare the reagents. So what are the reagents? The staining solution, the de-staining solution, and the proper mixture of protein. So you see over here, first we need to prepare the buffer. So either you need to weigh chemical and then measure with distilled water, or you simply need to mix the reagents that are provided in the kit to prepare the buffer. The exact amount is always shown. So first buffer is prepared, then we prepare Competency blue or amido black. Those are very black in color, and even Competency blue also looks like black. You need to prepare both staining solution and de-staining solution. So now decoloring solution is being prepared. So see, these are mixture of methanol and glacial acetic acid and distilled water. Alright, so first all these three should be prepared, okay. These should be prepared and refrigerated, because all electrophoresis experiment will generate a lot of heat, and all these experiments should be refrigerated. These reagents should be refrigerated. You need to maintain cool temperature, because warm temperature will degrade both DNA. Now the reagents are ready. So as I told you, they will be doing it in automated instrument. So see, these are serum protein samples, means samples from real patients. So first, how the samples are prepared? We mix certain amount of serum sample, okay. First the serum is isolated from blood, and then it is mixed with some amount of dye. The exact amount that is to be mixed is definitely written in the lab protocol. You see, the used tips are to be properly disposed, because these are serum, real human patients, and they can contain infective organisms, right. So the principle is mix some amount of serum and some amount of dye, okay. The amount of dye will actually guide us as to where we are applying the serum sample, because if you are doing it blindly, you will not have any idea, because serum is colorless, okay. So over here, see, they have already prepared the gel. or they are using a commercial gel. In this case, it is already commercially available. So what they are doing is they are using the instruction as per the kit. There is a specific, this is a specific sticker, okay, a colored sticker that will help us to identify where we are applying the samples. So first they are applying the colorless samples. Mind it, they are not using dyes. Okay, in Agarose gel I will be showing you that we are using dye. So sample has been applied. Okay, we allow some time to prepare. Now see, this is the electrophoresis chamber. This is very short chamber. Okay, it is not a big tank, but this is the mini tank. So what they will do over here, see, this is a positive electrode and this is a negative electrode. They will simply fold the gel in a U fashion so that the circuit is completed. So right now they are pouring buffer on the electrophoresis tank. So after the sample has been absorbed, you see the gel has already marked which area is positive and which area is negative. We need to be very careful while placing the gel. Okay, so the gel is placed in a U fashion and the circuit is complete, and now we are setting a specific voltage and time in the electrophoresis power supply. See, negative is connected to the negative and positive is connected to the positive. So after it is done, okay, again I will be showing you in a, see, negative is placed in the negative pole and positive is placed in the positive pole. This is an automated gel and we have folded the gel itself, right? So after the power supply run has ended, we will pick up the gel very carefully, not to fold, and it is placed in a fixer for a certain amount of time, which is NaOH. Okay, after the protein is fixed, we need to dry the protein, okay, in an incubator. After it is air dried, we will place it in a staining solution. So for around 6 to 8 minutes, okay, so after it is done, we will cut the staining solution. Now you can see protein has taken stains. Then we need to add the decolorizing or destaining solution, okay, which is a mixture of ethanol, methanol, glacial acetic acid and water. And now you can see this is the result. Okay, the result actually comes in densitometric analysis. I will be discussing with you shortly. So this is how an electrophoresis band will look like. This is the area where we have applied, so the dye is dense over here, and this is a part where it has migrated. So you can see there are different component band. So the thickest band is albumin and the thinner bands are globulin, alpha 2 beta, alpha 2 globulin, beta 2 globulin and gamma globulin. Alright, so these are the serum proteins that have been separated based on charge. Now we will again see another video of Agarose gel electrophoresis. Now let's go back to serum protein electrophoresis for a while. I told you, if the gel is put in a densitometer, okay, the densitometer will give a reading like that band, and that band is analyzed by a software to give the exact value, and from this value we will have an idea whether the serum protein pattern is normal or not. In normal individual, the albumin will be the highest and these will be the lowest. However, for you guys, you need to know a disease, that is multiple myeloma, in which gamma globulin will be high. So remember, write down this. So what is the use of serum protein electrophoresis? It helps us to diagnose diseases that can lead to defective serum protein pattern. So what are the diseases? You already know. I told you in nutrition video, marker of chronic liver disease is hypoalbuminemia, okay, low serum albumin. So in that case, serum albumin will be very low and other band will be high, and in multiple myeloma, gamma globulin will be very high. Remember, so in chronic liver disease and in nephrotic syndrome, albumin will be low and gamma globulin will be high. But in case of multiple myeloma, you will have an M band which is gamma globulin. So, in M band multiple myeloma, we will have specially gamma globulin level which will be excess high. Fine. Remember CLD, that is chronic liver disease and nephrotic syndrome, albumin will be low and globulin will be high. But specific gamma globulin will be very high in multiple myeloma, and we can diagnose these diseases with the help of serum protein electrophoresis. You should remember that this electrophoresis can also diagnose diseases of abnormal hemoglobinopathy, right? Those are sickle cell diseases, fine, and thalassemia also. So, hemoglobin electrophoresis can diagnose thalassemia, sickle cell anemia, those type of disorders. So, we are done with protein electrophoresis, but with protein electrophoresis comes agarose gel electrophoresis as a next question by the examiner. So, you should also know a bit of agarose gel electrophoresis because it is used to separate DNA, alright. So this is a demonstration by Biorad. So, see over here, this is the whole setup. So, we need the so this is a pipette, this is the pipette stand, these are the samples, this is the gel, this is a centrifuge, and this is the electrophoresis power supply. So, we will be needing them all one by one, may be not these one, this is done for PCR and this is used for preparing the DNA sample. So, that will be a separate video. So, we will move on, and this is the electrophoresis tank, okay. Over here you can see, if we place the buffer on both sides, see this is the negative electrode and this is the positive electrode. There are wires and the red color is positive and black color is negative. Mind it, sample will always move from black to red, okay, because black is negatively charged and our DNA or protein will also be negatively charged. Fine. We need to place the agarose gel on top of the tank. Okay, see the agarose gel is placed on the tank. Now, if the buffer is not, so there can be two ways, either you fill the whole thing with the buffer or you place the buffer so that is just below the tank and you place a filter paper and connect one end to the gel and another end to the buffer. In case of DNA, it is generally fully filled with the buffer. So, now you see we are filling the tank with the buffer. Watch closely, the buffer is filled in such a way so that it covers the entire gel. If it is not covering, suppose the buffer remains till here, then we need to connect it with the help of a moist filter paper. One end which will be here and another end will be connected to the buffer. But we are choosing to fill the whole electrophoresis tank with the buffer. See, we are filling the whole tank, keeping in mind that both sides and the gel are completely submerged, okay. These are the samples that have been prepared previously, and in this case DNA samples are prepared with the help of dye, okay. So, the DNA staining dye we need to mix the DNA staining dye with the DNA. These dyes are often fluorescent dyes and we will use a micro pipette. So, the DNA sample will look like a black dot because a small amount of DNA sample has already been mixed with the dye. So, it needs to be you need to press the plunger, okay, and then pick up the sample. Agarose gel has already wells, okay, there are small holes in the agarose gel that are made with the help of comb, okay, comb with which we brush our hair. Those wide teeth combs are placed in the gel first during the gel casting and these wells are prepared, and then we need to very carefully apply the DNA sample. They are heavy so that they settle down in the wells, okay. So, we need to apply the DNA sample into the wells one by one. This is very important. We should take care not to puncture the gel or not to apply in such a manner so that it spills. It's a very delicate procedure, DNA gel electrophoresis. After it is done, we will not move. Make sure you don't bump the whole thing. It should be very stable so that it will not spill. Then you will cover the lid, taking care black is in the black and red is in the red. Okay, this is basically a connection to the power supply, and the power supply has also color coded electrodes. So red should go into the red and black should go into the black. Okay, very important. That determines our direction of flow. After that, we will switch on the power supply and we need to set a constant voltage. Okay, you see over here the V is constant, so you can change the mode, either constant current or constant voltage. For DNA gel electrophoresis, we always choose constant voltage, and that is also depending on your lab protocol. So constant voltage is first set, and then if the machine supports timer, then a time is also set. Okay, depending on the standardized protocol. If there is no timer, we need to stand manually and see how far the DNA has gone. Alright, so next we will switch on the electrophoresis and immediately we will see bubbles coming out of the electrodes. Okay, you should note that the positive electrode has got less bubbles compared to the negative electrode, because you know more hydrogen is generated while electrolysis. So now we need to check in interval of 10 minutes or 15 minutes how far the gel has gone, how far the dye front is going. So this is known as the dye front. Dye front, F-R-O-N-T. This is the area where we have applied the DNA sample. So if the dye front goes towards this end, desired area, the area in between will have the desired DNA samples. So this is how the gel is done. The next step is this whole gel is taken out and it is placed in a UV transilluminator or a gel dock or a gel documentation system, and then we get the bands. So guys, this is in short how the both DNA gel electrophoresis and serum protein electrophoresis is done. So now again let us recap the steps and let us see whether now you can visualize the step or not. Okay, so either cellulose acetate paper, that is done in paper electrophoresis, or agarose gel is dissolved. I mean the gel is prepared first. So first the agarose powder needs to be dissolved in water, they need to be boiled and cooled, and the gel is done. We need to place the gel in the tank. Electrophoresis tank is uniformly filled with buffer. Okay, sample is applied transversely using an applicator. Buffer soaked filter paper is placed on as wicks, overlapping, either one side in contact with gel and another side in contact with the buffer, or we may choose to fill the whole thing with the buffer. Then the chamber is connected to the power supply and it is run. After this, the whole thing is disconnected. In case of protein electrophoresis, then we place it in a fixator, that is NaOH, and then we need to place it in a staining solution followed by a destaining solution and then a densitometric analysis, which will lead to this type of figure and band. And the applied importance is these one: multiple myeloma, M band, gamma globulin, and chronic liver disease and nephrotic syndrome, albumin and low albumin and high globulin. Often one MCQ question comes, that is, which of these is not a part of electrophoresis apparatus? So minded, these are the essential, anything else will not be part of electrophoresis. Electrophoresis tank, electrophoretic support. Now you know how these things are used, that is the gel, power supply, filter paper, buffer, staining solution, destaining solution, and a fixator. What are the factors on which migration of a charged particle depends? Net charge, mass, strength of electric field, pH and viscosity, and lastly the principle of electrophoresis. This will be asked in Viva. So guys, this was it. Thanks for watching. Feel free to get back to me in the comment section with any query, and I will see you in the next one. Till then, bye and take care.